Yeah, so after I woke up from like 4 hours of sleep, I made a lot of errors in that last video. I'm sure everybody who looks at it, both of you, will notice that. But I tried as I'm going along, and as I noticed them, I tried to correct them. But after waking up from a few hours of sleep, taking care of all the animals and gardening and all that shit, disposing of captured rats and things, um, I took a little bit more detailed look at approximating base E and trying to do it sort of as simply as possible. All right, so we saw that this worked really, really well, right? 3323323, and the approximation of this, which occurs in see, I'll do it on this line, which occurs in USCS fluid units, is like this. Right, and that's actually where I got this from. So this is 4222 423. So what I did is I just swap over 1 from this 4 added to this 2, swap over 1 from this 4 added to this 2, and now it's almost patterned, right? This 323 unit is sort of just in there. And if we use 323 as our base unit, then this 3 actually makes sense. It would be the next thing in there. So this actually looked like, hey, maybe we can actually simplify this to base 323, right? So that first component of the digit operates as if it's ternary, the next one operates as if it's binary, and then the last one operates as if it's ternary. So the first one, ternary, and you would write it in a practical number system, it would look like 10, right? But the actual value of 3, right? This is a pretty fair approximation of E in every sense. It's the closest you're going to be able to get to with an integer, right? Because E is closer to 3 than it is to 2, and 3 to the first is the same as 3, and E to the first is the same as E. So, yeah, in every sense, this is a fair approximation. Now, when we go to the next one, which would practically be written as, it would look like 100, something like that. Or however you want your number system to be devised. There's lots of ways to do this, which is sort of the problem with a naive look at number bases, because like the new math sort of approach to looking at number bases, it just says that within a base, you have a digit, and there has to be the base number of them, right? So if you're in base 10, then you have to have 10 distinct looking digits. And that's not wrong. That is true. But we can make things more elegant than that. So that's kind of what I'm getting at here. So when we throw on that binary one as sort of our like tens place, right, to our ternary ones place, it would be written out something like 100. And there's ways to optimize that to make it look nicer. This is going to yield a per digit average of 2.5, which is closer to E than 3 was. And our 100 value is going to be 6, which, as an approximation of E squared, is not that far off. E squared is 7.4, basically, just shy of 7.4. Now we add our next one, 3, our next ternary unit, so we get a full 323 cycle. So we're now at, like, effectively this is base 18, because 3 times 2 times 3 is 18. So effectively we're operating in a base 18 system here. And we've just subdivided that into a ternary, binary, and ternary subsystem. So this is going to be written as, depending on how you look at it, this might actually be what's written as 10. But because there's nothing on this side, and we have one full unit of that. So this yields a per digit average of 2 2/3, which is even closer to E. And 18 is its approximation of E cubed, and E cubed is 20.1, just under 20.1. So you might note here that base 20 is actually a pretty nice base to use if we're considering efficiency. So then we come out a little bit more and we get a per digit average of 2 3/4. That yields, at this scale, we're getting 54 as our approximation of e to the fourth, which is amazingly close because e to the fourth is actually like 54.6. It's really, really fucking close. One thing that's going to happen is we're always going to be under. So we're not... This doesn't approximate it so well that like we keep going over and under and over and under and over and under. And it doesn't approximate it so well that it converges. So it is always under and it does diverge. But out pretty far, it's going to work pretty well. So now our next thing that we add, because the last thing we added was a 3, the next thing we're going to add is a 2. So we're just going to double it. So obviously our approximation is going to be 108. But e to the fifth is 148. So now we're starting to get a little bit off there. We're off by like kind of a lot. But your per digit average is 2 3/5, which is quite close to E. And then we add on another 3, and now our per digit average is 2 2/3, which is quite close to E. This gives us 324 as our approximation of e to the sixth. E to the sixth is actually 403.4. So kind of far off, but not far enough off that we actually will need a new digit. All right, that's kind of the important thing. The important thing is that we're not yet far enough away to actually need a new digit to represent these numbers. Because to need a new digit to represent these numbers, we have to be off by a factor of like 3, right? Well, a factor of e, really. So this next one, e to the seventh, is actually the one that we looked at in the last video. So our per digit average is 2 5/7, which is extraordinarily close to e. But this yields 972 as our approximation of e to the seventh. You might notice, though, that by swapping the 3's in for the 2's, for 2 of the 2's, and for 2 of the 4's, that actually brought us up. It was like 720 or something. Yeah, it was in the 700s. So that actually brought us closer. So you can see sort of what the efficiency is meaning. That approximation of E in terms of efficiency, what that actually means. Because when I bring these all closer to E, instead of having 2's and 4's, I have, for any pair of 2 and 4, I just average them both out to 3. That did actually bring our approximation of e to the seventh closer, which makes sense. So here e to the seventh is actually 196 points, or 1096.6, and we're estimating it as 972. So we're pretty far off, but in terms of like raw value, but not really in terms of needing a new digit yet. And you actually have to go out pretty far to need a new digit. So at 8, we get a per digit average of 2 5/8. And it is interesting, actually, that the denominator in these fractions always correlates to the number of digits that we have. Right? So we have 8 digits. There's an 8 in the denominator. We have 7 digits. There's a 7 in the denominator. There's 6 digits. There's a 3 in the denominator, but that's because the numerator was even. Here there were 5 digits, and there's a 5 in the denominator, a 4 in the denominator, a 3 in the denominator, a 2 in the denominator, right? It's because of how this works, right? Here we would have a 9, but again, it's divisible by 3, right? And every time you get a full cycle, a full Base-18 cycle, it's gonna be 2 2/3, right? Every single time we get a 3-2-3 completed, it always comes back to an approximation of E of 2 2/3. So 2.666666, etc., right? When E is 2.7, whatever. And that's actually pretty much You can see from that that's why we're never going to, oh, we're not converging on E. We're converging on 2 2/3 actually. Yeah, so that one, it's off by quite a bit. By the time you get 9, let's see, 8 was yielded in 1944 as an approximation of 2980. That's pretty bad. 9 digits yields 5832 as an approximation of 8103. That's pretty bad. It's pretty bad. But your per digit averages are sitting close to E. So there is some real efficiency that is actually being gained here. Also, it's very simple. It's very simple to learn this. We're just, it's not some convoluted pattern that like, oh, the 17th decimal place, it has to be a 2. While like the previous 3 have to be a 3. It's not some crazy shit like that. It's just a repeating 3 2 3. So in that regard, this is very simple, very efficient. And that is a level of efficiency that isn't really captured in the logic of the efficiency argument. So I'm not even sure how to fully analyze it, but there is something gained here by just blocking this Base-18 thing. So then looking at it a little bit more, predictively, right? So e to the first is 2.7182818284590452. That makes base 3 a reasonably efficient number base. As far as integers go, it's the closest you're going to get to e. It's beautiful, right? But now note that since the ln of 5 is 1.61 whatever, base 5 is maximally inefficient for an integer base at this scale. But now note that in my numerals, they resolved this inefficiency by using only 3 symbols. They had a symbol for 0, they had a symbol for 1, and they had a symbol for 5. And what they did is they would just write up to 4 1s to indicate 1, 2, 3, and 4. But they're only using 3 symbols. So they're using the maximally efficient number of symbols with the maximally inefficient integer base. So it's not maximally inefficient. What they did is, by using an approach like what I'm doing here, by blending systems, they increased its efficiency, right? Because the naive approach is you have your number base indicates the number of symbols you have, but that's not what they're doing. They don't have 5 distinct symbols. They have 3. And actually, yeah, by the time you get the 3, including the 0, you actually sort of have a base 6, in a sense. It's not really, but kind of. Which is actually less efficient than base 5. So, yeah, like, there's some nuance to this that actually makes it cleaner than just a base 5, the way that it is being classically analyzed here, under, like, 1960s era new math. Yeah, so e squared is 7.4 whatever, a little less than that, 7.389. So this actually makes base 10 obviously very inefficient, because 10 is pretty far from that. And now if we look at the ln of 10, it's 2.3 something. So base 10 is close to being maximally inefficient. Now if we search for our maximally inefficient thing, so this is going to be as far away from an integer power of e as possible, so that's going to be 2.5 in this case. E to the 2.5 gives us just over 12, like 12.18. So this means that the simple base 12 is maximally inefficient for an integer base. But we can use tricks to easily compose base 12 in several more efficient ways. So you could use something like a 223, 232, 322, something like that, where you're breaking it up into 3 parts. Or you could use a 4-3 or a 3-4, something like that. Or you could sort of use a Mayan approach where you reduce the number of symbols that you're using, and you bring the number of symbols much closer to E, right? So this 2-2-3 approach you only need 3 symbols. So now it's very, very efficient in terms of the number of symbols that are being utilized. And it's approximating E. But now notice E cubed. It's just over 20. It's 20.08, 20.09 if we round it. This makes base 20 a very efficient number base. And you might also notice that the Mayan number system, for the most part, used base 20. There are some actual parts in the Mayan number system that use base 18, though. So that is also interesting, where 18 is sort of what we landed on here. So that is interesting. And they weren't landing on these because they were thinking about this in this way. You know, they didn't have this philosophy about it. They didn't know about E at all. They're landing on it for some other reason. There's something driving number systems in practical use towards this that people aren't aware of. Right? So now we kind of play around and look for where using our base 18 system, right? So our e to the base 18 versus E cubed. At what point do we need an extra digit, right? So I just kind of grabbed one. So like you can see it's diverging just by here, right? So e to the 9th is E cubed cubed. So we need to go out a little further than that. So I started at E cubed to the 5th. That gives us these values. So we're like, what? E cubed to the 5th is like 3.27 million. And 18 to the 5th is right around 1.9 million. So their ratio to each other is the larger one, which is the E, 1.73 to 1. Okay, so that's not great, but it is less than either 2 or 3. So we're still not going to be getting an extra digit because of this, regardless of where we're at in the cycle. So it went out a little bit further. Try 8. So at 8, the values we get, the ratio we get is like 2.4 to 1. That's pretty close. It's pretty close. So probably the next one, we're probably hitting on something here. When we go to the 9th, so this is going to be 9 full positions of 323s, 9 full cycles of that. So this is a big ass number, right? We're looking at, let's see, what is this? Half a trillion. At the scale of about half a trillion, our ratio is 2.68 to 1. So we're real close to needing an extra digit here. And in the next one, when we go out one more, we get to the point where we've exceeded E to 1. So at this point, base 323 or base 18 requires 1 extra digit compared to base E. But it is also worth noting that base E is extraordinarily impractical. It is sort of our ideal for efficiency in these naive terms, but it is exceptionally impractical because just writing out the number 3 requires an infinite number of digits. And it's actually just an inverse of the problem that writing E in our current number system requires an infinite number of digits. It's the same exact problem, which just been where the problem appears just got reversed. That's it. And for any integer larger than E, that's going to be the situation. And since we primarily operate in integers, that's not nice. That's not nice. So needing 1 extra digit compared to base E, there's caveats that come with that. Right? Because it's sort of not actually ever true. Right? Either your base 18 is working magnificently, or your base E is working magnificently. They can't both be at the same time working well, right? One of them needs infinite digits, or the other one needs infinite digits, depending on which number you're trying to represent. So, yeah. Yeah, I thought that was interesting. There's some interesting things in there. And it sort of highlights some nuance that I haven't really seen people talk about. I see people talk about just, that classic, like,
In binary, you have 2 symbols. In ternary, you have 3 symbols. In decimal, you have 10 symbols.
it's not true. Because in Mayan base 20, there's only 3 symbols. Right? Like, and it's a positional number system with 0. So it operates very, very, very analogously to our base 10 system. Almost identically. Like, the learning curve is fucking almost nothing. But in our base 10 system, we have 10 symbols. Whereas in Mayan base 20, there's 3 symbols. And note that base 20 is exceptionally close to E cubed, and that 3 symbols is exceptionally close to E. So their number system, their numeral system, is objectively, in some specific ways of thinking about it, massively more efficient than base 10. Particularly since, so base 10 is close to being maximally inefficient, but it's also the way we use it. We literally do use 10 distinct symbols: 4, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, which keeps us there. Which keeps us very close to being maximally inefficient, right? Base 5 is maximally inefficient, but the Mayan numeral system only uses 3 symbols, so that brings its inefficiency down. It increases its efficiency. And then that is set within a base 20, which is exceptionally efficient. So, yeah, go ahead. Tell me the metric is better. You're wrong.